Welcome PCS members and friends to our today's PCS IBS seminar. It is a great pleasure to have with us today Dr. Oleksandr Marchukov, and I would like to invite our scientific host Sergey to introduce our speaker. Please, Sergey.
Yes, hello everyone. It's a pleasure to host our today's PCS seminar. Our speaker is Dr. Oleksandr Marchukov. Let me say a few words about him. He did his undergrad and master studies at the Karazin Kharkiv National University in Ukraine. And then in 2012, he moved to Aarhus University in Denmark, where he did his PhD. And which he finished in 2015, and then he moved to, he was at several places. Apparently he worked for 1 year at Seoul, at SNU, at Seoul National University in Korea, from where on he moved to Tel Aviv University in Israel, from 17 to 19. And the main era of the worldwide pandemics, he spent at the Technische Universität Darmstadt at the Institut für angewandte Physik, where he is also located right now. And Oleksandr will give us a talk today on solitons and cold atomic gases and quantum fluctuations. So please, Oleksandr, the floor is yours.
Thank you very much. Thank you for this kind introduction. And it's a pleasure to give a talk about my work with solitons. That was done in Tel Aviv University mostly and finished in TU Darmstadt, where indeed I spent most time of the pandemic and still do. Well, I'm in home office now, so, but close enough. Right, so I'm going to talk about solitons in cold atomic gases, in Bose gases in one dimension, and quantum fluctuations. So the outline of my talk is the following. So first I'll introduce solitons as the concept, and specifically solitons in Bose-Einstein condensates. I'll later talk about nonlinear Schrödinger equation, which is the workhorse of theoreticians in this problem. Then I'll describe the method to calculate quantum fluctuations on the example of a fundamental soliton. After that, I'll show our results for a breezer, which is a system of two solitons. I'll talk more about it further, and I will conclude. So solitons are localized nonlinear waves that satisfy two criteria. They don't change their shape when they move. And upon collision, two solitons don't change their shape. They may have phase shift, but like as you can see from this animation, after the collision, they maintain their shape. They are very ubiquitous in physics and in nature. So there are basically in almost every sub-branch of physics, you can find an example of solitons, from water waves to Bose-Einstein condensates, which is of most interest to me and my collaborators on this, to biophysics and to many, many others. So for the first time in 1834, the solitary wave, so predecessor in a way of solitons, was observed by Scottish engineer John Scott Russell, who observed a rounded, smooth, and well-defined heap of water which continued its course along the channel, apparently without change of form or diminution of speed, in a water channel in Scotland. He tried to follow this well-defined heap of water on his horse, but at some point lost it in the channels of Scotland. And he was very interested in this phenomenon, and he tried to reproduce it in his lab. And on the left, you can see some sketches from his publication, which are done by hand. There's no mathematical matplotlib. It was much simpler and beautiful time, I guess. I'm joking, but yeah, you can find these papers, for instance, online, and they're very interesting to read, and they're very beautiful to see the pictures. And yeah, so 150 years later, this solitary wave that Russell has observed was recreated in the same channel. And on the right, you can see the photo from this recreation to the astounded crowd. So Russell's observation led to a lot of controversy. Many theoreticians of the time, let's say, were not sure that this phenomenon is real until in 1877 and then 1895, the equation to describe solitary waves was discovered by first Bose and then de Vries. And for a long time, that was basically the end of the story. Until in 1965, Zabusky and Kruskov discovered solitons, so these particle-like waves, let's say, when they were simulating de Vries equations numerically. And so this is their publication and the figure from their numerical calculation. So they observed the surprising particle-like behavior of these individual solitary waves, and hence they named them solitons. As I mentioned before, so the surprising behavior is that, that the solitons do not change their shape when they collide. So we are, as I said, most interested in solitons in Bose-Einstein condensates, and which is the condensed gas of bosons in the lowest available energy state. And the workhorse for Bose-Einstein condensates of dilute alkali gases, for instance, for very cold gases, is the Gross-Pitaevsky equation.
Alexander, we have a question from Dominic.
Yeah, sure. Yeah, sure.
Sure.
Could you speak? Could you please say more about solitons? Like, how do I know that something is a soliton? What is the requirement for me to call it a soliton, for example? And in which systems do they happen? Like in which systems?
That's a very good question. That's an excellent question. So there are two kind of sides of the story. So in principle, there are mathematical solitons that you can find solving nonlinear equations. Where you have integrable system, and I'll talk a little bit about this later. You can find the solution, the set of solutions that mathematically can be called solitons. Physically, we are as usual a little bit less rigorous, let's say. And so if oftentimes I would say that if your physical wave kind of follows this behavior, then it's considered a soliton. So for instance, in experiments with Bose-Einstein condensates, so the nonlinear Schrödinger solitons, they are always in 1D, but we don't have experiments in 1D, we have quasi 1D. But the behavior of localized wave packages, let's say, is very similar to those of the mathematical solitons, and thus we name them solitons. I hope that answers.
Well, so what is the difference between a wave packet and a soliton?
Well, wave packet can disperse. So in soliton, you have dispersion that is balanced by the nonlinearity, and so it maintains its shape through motion. So you see, like in Gross-Pitaevsky equation.
The wave packet disperses.
Genau, yeah, exactly, yeah.
Oh, I see.
So you see,
the soliton is basically a wave that doesn't change; it's kind of localized.
Exactly, yeah. So for instance, here in Gross-Pitaevsky equation, here's the usual kinetic term, but here's the nonlinearity, and due to this minus sign, it actually balances. The dispersion is balanced by the self-focusing.
Mm-hmm. So these things cannot happen in like usual Schrödinger equation.
Yeah, for this you need nonlinear Schrödinger equation. Yeah, and again, that's something I'm going to talk about like in a few slides.
Okay, very good. Thank you.
Yeah, thank you.
Let me add a bit to the confusion here, because I just remember there's one linear equation which allows for quote-unquote solitons, which is the so-called wave equation. No? So dx squared minus dt squared. Because the group velocities don't depend on the wave number, you can form any kind of wave packet, and that thing will move with a constant speed.
Yeah,
but that's just a nasty remark, which probably So the reason why usually wave packets don't stay compact or localized is because the group velocities are different for different wave numbers or vectors, which are all put into one structure which is localized in real space. But there are exceptions.
True. I mean, yeah, in principle, yes. So so when we talk about solitons, we usually think about nonlinear equations. So that's, I guess, my point. But you're absolutely right. Yeah.
There's another question there up now.
Sure.
Hello. So you have mentioned the Kordovec-de Vries equation as well, I guess, explaining solitons and also the nonlinear Schrödinger. So is there a mapping? My question is there a mapping? And if there is no mapping, then what can I say about solutions? Are they exactly same solutions, or do they satisfy some exactly same criteria, so you can call them solitons?
I will talk a little bit about solutions of nonlinear Schrödinger and in principle how you approach. So the point is, so there are different solutions for Kordovec-de Vries and nonlinear Schrödinger, and so there are kind of families of nonlinear differential equations that excuse me that are integrable in a way that you can find the analytic solution using the so-called inverse scattering method. Again, I'll mention briefly in the next few slides. But yeah, they're in the same family because you can find these exact solution, like analytical solutions, more or less, of the family of solutions, because they have infinitely many conservation laws, and that leads to the infinitely many kind of soliton-like solutions. But so they exhibit similar behavior as solitons, but they are different. So, for instance, the simple example of this, I guess, there is also sine-Godon equation, which looks like Klein-Godon but with sine, so it's a pun. And it also has soliton solutions, and even more so, you can have two solitons in the bound state, so to speak, in a breezer, again, something I'm going to talk about later today. And for sine-Godon equation, the breezers, so the solitons in the breezer, they have negative bound energy. But nonlinear Schrödinger equations also has breezers with zero bounding energy. So there are differences in this, but there are many similarities due to the integrability and mathematical structure of these equations.
So okay, then a follow-up. When you say that there is a solution which belongs to soliton family, basically, can I say that any solution which doesn't disperse is a soliton?
I don't think so. I mean, also the another characteristic is that if the two solutions, or if the two waves collide and they exchange places, basically they maintain their shape, then you can. I think it's fair to call a soliton.
Okay, thank you.
Thank you. Okay, shall I continue?
Yes, please.
Right. So, as I said, we are interested in solitons in Bose-Einstein condensates, and the equation that governs the evolution and evolution of the systems, at least in in dilute alkali gases, for not very strong interactions, is the Gross-Petersky equation. Bose-Einstein condensates experimentally were around since 1995, and so the Gross-Petersky equation describes the dynamics pretty well. So this is figure from one of the first experiments from the group that did one of the first experiments in Bose-Einstein condensates. And if you ever heard talk about Bose-Einstein condensates, you've seen this picture. I think at this point it's illegal to make a presentation about Bose-Einstein condensates without this picture. And it shows that it's the Gauss distribution for different temperatures. And it shows that indeed for low temperatures, the atoms, they condense in the lowest energy allowed state. What's interesting about the systems, the Bose-Einstein condensates, specifically called atoms, is that you have a lot of control of the parameters. And as an example, you can control the interaction strengths, the nonlinearity in Gross-Petersky equation. by the methods of Feshbach resonance. So it's a knob that you can use. And that allows the experimentalists or theoreticians to go into different regimes and consider different situations, of course. Right, so yeah. So the solitons in Bose-Einstein condensates has been around for some times. They were experimentally realized more than 10 years ago for the first time, if I'm not mistaken. And the idea is that you first create a stable Bose-Einstein condensate with the repulsive interaction, and then you change via the Feshbach resonance or some other methods the sign of the interaction, thus producing the attractive BEC, which produces these soliton trains. So this is the figures from the experimental papers, the experimental results. And yeah, so those are solitons in physical sense. Yeah, so Gross-Pedievsky equation is mathematically nonlinear Schrödinger equation. And as I mentioned to answer the question, it's integrable, the nonlinear Schrödinger equation, and it has infinitely many conservation laws and soliton solutions. And it was first discovered by Zakharov and Shabbat in 73 in this paper. And that led to a lot of activity in mathematical physics, considering nonlinear differential equations. And specifically, it led to creation of the inverse scattering transform by Gardner, Green, Kruskal, and Miura. And in few words, and very few words, the idea method is that in principle, if you want to solve a nonlinear partial differential equation, you have initial data, you need to solve it, and you arrive at the final data. So they realized that for certain problems, and nonlinear Schrödinger equation is one of them, you can make a so-called scattering transform. Taking your initial data is the potential for a scattering problem. Then you arrive at the linear differential equation that is a scattering problem, which is usually simple or sometimes simpler to solve. You can solve it, and then you make the inverse scattering transform to final data. Thus, you kind of go around the problem of solving a linear partial differential equation. So yeah, that's the method used to approach the linear differential equations like the linear Schrödinger equation.
Oleksandr, I have a question at this.
Yes.
Can you comment which is the hardest part of these three steps going around? Well, if you did it by yourself, because I never did it by myself, so I have no idea.
I did it partly. So I mean, for this problem, I didn't work with nonlinear with inverse scattering transform. I think the inverse scattering transform would be the hardest. Sometimes it also depends on the equation, I guess, because so this part is relatively simple because it's mapping to the just a potential. You can redefine. It's usually. I don't want to say something that is not very this is arguable, you know. But for nonlinear Schrödinger, I think it's relatively simple. And then then you need to solve linear differential equation. But yeah, you can do it numerically, for instance, or analytically. And then the inverse scattering transform can be, I think, a little bit more tricky. But also, it's good. This method is good because you kind of have the steps more or less pointed out.
Mm-hmm. Thank you. There's a question by Alexei. Please, Alexei.
Yep.
Yeah, can you hear me?
Barely, but yeah.
Okay.
Louder, please, Alexei. We don't hear you.
Is it any better?
No.
A little bit. Oh.
Then,
yes.
Is it better now?
Yeah, now it's better.
Okay. Yeah, I'm just curious. Is the scattering transform in any way related to the isospectral transformations? because all I know about this, say, the Korteweg-de Vries equation is that it can be derived by imposing that a certain, basically a linear problem has a spectrum that doesn't change until the deformations of some potential.
Okay, I am not expert in this question. I think it feels connected in a way because yeah, again, you map it to linear problems, so I guess in this way it's connected. But I don't think I should answer it to not say something very wrong.
Okay. Okay.
Yeah, sorry.
No worries.
Okay. That's it, I think. Anyway, then I'll go on. Right. So why do we care about solitons in BECs? This is because, and I'll run this again. This is because a Bose-Einstein condensate is a quantum phenomena. It's a macroscopic quantum phenomena. And specifically, our results discuss the dissociation of a two-soliton system and the influence of quantum effects of quantum fluctuations. Thus, observing this is observing of macroscopic quantum phenomena, which is always an interesting thing. There are not that many macroscopic quantum phenomena that can be observed. So that's our main interest in this. Okay, so as I said, we are preoccupied with the quantum fluctuations of the solitons and soliton systems. And for that, we can quantize the nonlinear Schrödinger equation, the classical nonlinear Schrödinger equation, using quantum field creation annihilation operators that are following the regular bosonic mediation relations. So there is a connection to nonlinear optics. The similar approaches were used in the solitons in nonlinear optics, and there are some publications about that. But as Feynman taught us, same equations have same solutions. So yeah, there is this similarity that I think needed to be mentioned. Anyway, so how do we approach finding quantum fluctuations on solitons? We employ Bogoliubov-like methods, linearizing our quantum field, saying that most of it is classical solution of nonlinear Schrödinger equation with some quantum part that corresponds to annihilation operator, quantum fluctuation annihilation operator. And the classical field solution can be either a fundamental soliton, two-soliton solution, or higher order soliton solutions. So let's discuss it on the example of single soliton, fundamental soliton. There is a solution which is given here. And there are 4 parameters that describe the solution. It's number of atoms, its global phase, its velocity, its center of mass velocity, and the coordinate to center of mass. So yeah, so the linearization works in the following way. And we separate the quantum field into the classical part and the quantum part. And this linearization obviously linearizes the nonlinear Schrödinger equation. And we can use the expansion of delta psi as in terms of the operator on which the solution excuse me depends on.
So Alexander, we have a question.
Yeah.
From Aura.
Yeah, it's in chat.
Yeah, I would like to ask whether you have solitons also in superconductors.
In some systems, I guess, yeah, I'm not sure for superconductors. Right now, from the top of my head, but I'm sure they are.
Because the technical treatment seems to be very much the same.
Yeah, but that's more because it's sort of a quantum field theory and the Bogoliubov method. So in this way, so in this point, at this point we don't really say about solitons. Nothing except that yeah, we use nonlinear Schrödinger equation that can have solitonic solutions.
Thank you.
So yeah, thank you. Right. So we can expand delta psi operator in terms of the fluctuations of the parameters that the classical solution depends on. Here, these modes of expansion are the derivatives of the solution for the parameters. And one way to think about this, operators is in terms of Goldstone and lost modes. So in Bogoliubov treatment, the dot of psi should obey the equation written here. And so the eigenproblem for the Liouvillean or Bogoliubov-Desgen has also solutions with zero energy. So the Goldstone, they correspond to the Goldstone bosons. But even with adding Goldstone modes to the basis of Bogoliubov modes, the basis is not full, and from completeness conditions, you find the lost eigenstates. My point being that, so this is the usual Bogoliubov modes, which are continuous, and the four discrete, so to speak, modes, they come from Goldstone and lost modes. Or rather, you can relate them, but the spirit is in this venue. So the expansion modes of chi are not orthogonal in the usual sense, but we can sort of orthogonize them. We can introduce the quasi-inner product. And yeah, so that it follows this orthogonality, and this orthogonality will help us to calculate the fluctuations in the future. Also, the parameters are combined into pairs, which is quite natural, I would say. So it's number of atom and phase, and velocity and coordinate. Also, we assume that the discrete fluctuations are orthogonal, or modes of expansion are orthogonal to continuum fluctuations. That meaning that continuum fluctuations don't affect the fluctuations of discrete parameters. And there are two reasons for that. So from nonlinear optics, we know that for the infinitely long time, these continuum modes disperse. And also, if you construct Bogoliubov's eigenstates rigorously, they are orthogonal by definition. So this is like to show this fact. So for now, it's an assumption. To show this rigorously is something that we are, my collaborators and I, working right now also. But there are good reasons to believe that. Thus, we can express the operators for the parameters using the orthogonality of the modes, and through this we can derive the variances of the parameters, which would be proportional to the averages of the quadratic squares of the creation and relation operators. So when we talk about this, so when we talk about averaging, we talk about averaging of vacuum states, and here it's a hard product states, meaning that we have a vacuum is a classical vacuum is a solution that is a Hartree state that combined of atoms all sitting in the state that is a soliton, and that means that only one of the products survives. So of averaging, all others give you zero. And thus we can arrive at a very simple and neat formula for the variances of quantum fluctuations and calculate them. So this is just analytical calculation that you can calculate the variances, the values of the fluctuations of the parameters at T0 and in principle at any T, but T0 is the most interesting for us. This has been done before. Again, this part I just tried to explain the method that we would use for the more complicated system. So we can, using this variances, we can look at the uncertainty relations for fundamental soliton, and they follow. So the interesting thing here is that the uncertainty in momentum economy is very close to the quantum limit, and that it comes from the fact that here's the comparison, that the shape of a soliton is very close to a coherent state, the minimum uncertainty state, but the uncertainty of the soliton is a little bit higher. So that's just a neat fact. But yeah, our work was focused on the nonlinear superposition of two solitons, so-called BRIZA. So in this superposition, you have two solitons with the amplitude ratio 1:3, sitting in the same, locating at the same spot. And so here is the 3D plot of this of the system. So it's still localized in space, meaning that it doesn't move, but it changes. It has this breathing kind of behavior. Yeah, so we can look at it here. So red one is the usual fundamental soliton. Blue one is the two solitons with the ratio 1:3 sitting on top of each other. And yeah, the name BRIZA comes from the behavior that we can see here. Why is it important? Why is it interesting for us? Because again, in Bose-Einstein condensates, in Bose gases, in quasi-1D Bose gases, there were recent experiments in which BRIZAs were realized. So in 2019, the group from Glasgow was the first one to realize these BRIZAs. And a group in Texas, with which we collaborated, last year realized two soliton BRIZAs and three solitons BRIZAs. So when three solitons sit on top of each other, and the amplitude ratio is 1:4:9.
Oleksandr, can you comment what happens if you choose these two solitons in this previous example? You said with a ratio 1:3 in their frequencies, right? Or
the amplitude, yeah.
What happens if you choose another ratio?
Well, what I'm saying is that this ratio 1:3 comes from mathematics. So it's a mathematical solution that gives you this breathing behavior. So if you have there are several ways that can happen. So for instance, system can shed all the the density that is in return to 1:3 ratio, for example, or they can just separate as two different solitons. So if the ratio is close to 1:3, you would have a BRIZA, but maybe with some phonons running around, something like that.
I see. So if you deviate from these specific ratios, then you get some background radiation, so to say.
Yeah. Usually, I think that's true. It's very since mathematical reason for this is integrability. It's very robust under this thing. So, for instance, in the experiments, okay, this one, the ratio was not exactly 1:4, but close enough, and they can see the BRIZA-like behavior.
Thank you.
Yeah, thank you. Okay, so yeah, as I mentioned before, a BRIZA is you can consider BRIZA a bound state, so to speak, of two solitons with zero energy. It is more of an analogy than a strict statement, but that's something like a picture to have in your head. So you have BRIZA is two solitons sitting on top of each other, but they kind of happen to sit there. And so our point is that perturbation from external perturbation or internal, meaning the quantum fluctuations over BRIZA, can separate the BRIZA into daughter solitons, the solitons that it consists of. So here, for instance, 1:3. So that's the picture that we want to see after separating the BRIZA or dissociating the BRIZA. Oh yeah. So from the inverse scattering method, it's possible to find a two soliton solution. So exact solution that was done by Gordon last century. And yeah, it's not easy to follow, but you can kind of see that it's the superposition, nonlinear one, of two solitons. Indeed. So this is general solution, meaning that special cases would be like one soliton and the BRIZA. But in principle, the solution also describes dynamics of two nonlinear Schrödinger solitons of any amplitude of any parameter. So you can, for instance, describe as a solution also the collision of solitons.
Can I ask what is the small n here?
N is a relative number of atoms in each soliton. Next slide is going to talk about this. Yeah. So yeah, that's a good point. It's actually something I should have mentioned. So the point to have this here, that yeah, we have a classical solution which we can use for our linearization scheme, and there are parameters, rather 8 parameters, on which the solution depends on, which we can use for our linearization scheme again. So indeed, there are 8 parameters: 4 for center of mass and 4 for the relative between two solitons that a breezer consists of. So yeah, the solution is due to Gordon from this paper. And yeah, so the parameters are the number of atoms, the overall phase, the center of mass velocity, and the center of mass position, and the relative number of atoms of two solitons, relative phase between solitons, relative velocity, and position. But then, yeah, we just apply the same linearization scheme that for fundamental soliton, now using 8 parameters instead of 4, with the same quasi-orthogonality. And yeah, we can calculate the initial variances of breezer parameters. They are different than for one soliton, except for, so they're for the, but they're different but similar in a way that, for instance, this one holds for fundamental soliton and for breezer. Because if you look right here, at t equals 0, the shape of a breezer and the soliton is the same. Then it changes, but like for initial variances, it does not. Yes, right. The uncertainty relations still hold. Yeah, and we are most interested in the relative velocity fluctuation, because that's the fluctuation that arguably can show you how fast a breezer would dissociate. So one of the amendments to what we did with the soliton is the following. So first of all, how do you create breezer from a soliton? From the symmetries of the nonlinear Schrödinger equation, you can show that if you change the interaction constant exactly 4 times, your soliton solution becomes a breezer. So it would show this breezing behavior. And as I said before, so for one soliton, we used vacuum state as the Hartree fork, so there was no correlations in it. We can include the quantum fluctuations on top of the mother breezer, so before quench, into the vacuum state to calculate the fluctuations of the parameters for a breezer. That's exactly what we do. What the problem is here that now, if for white noise you only have one product that is not 0. For the correlated noise, all of them you have to include, and so the calculations are a little bit more complicated, but manageable. And so, what's the difference then? The difference then is that the the initial fluctuations of the relative parameters of a breezer, the results are different for white noise and for correlated vacuum. And in this table, you can see the difference, and also the comparison with the extrapolation from beta ansatz. So in this paper, my collaborators before my time calculated these parameters from beta ansatz for 21 particles, for 21 atoms, if I'm not mistaken, and then extrapolated it to the thermodynamic limit. And you can see that if you include the correlations of the mother soliton, the results of this Bogolubov scheme are much closer to beta ansatz than for white noise. So it's an improvement, which is important for experimentalists. So we can predict better how long time do they need to have a breezer, solitons have a breezer stable. So yeah, as I said, delta V0 squared, so the fluctuation of the relative velocity, is the most important for us because we can introduce the dissociation time, tau, which is time that it takes a breezer to separate into two solitons. And for the realistic parameters of the experiment, say in Texas, you can calculate it to be around 4 seconds, around 4.5 seconds. And again, the correlated noise gives larger time and closer to beta ansatz. And that is important because it is it's quite hard to keep attractive BEC from collapsing. And thus you need to have better idea of how long do you need to do this. But that is observable, and which comes purely from quantum effect, and so that is macroscopic quantum effect. To conclude, our linearization allows us to estimate quantum fluctuations of the parameters of solitons, of Breezer. So in principle, the three soliton breezes and so on. And we can include the fluctuations of the mother soliton to get a better value, so closer to the extrapolation from beta ansatz. These fluctuations indeed dissociate a breezer, and we can evaluate how long does it take for a breezer to dissociate under just the influence of quantum fluctuations. I would like to mention people who I collaborated with. So it's Boris Malamet, Vladimir Yarovsky in Tel Aviv University, John Rowe, Vanya Dunko, and Maxim Valshany in UMass Boston from the theory side, and Henry Guo, Eva Jean, Jason Nguyen, and Randy Hewlett in Rice University from the experimental side. And with this, I would like to thank you for your attention.
Thank you, Oleksandr, for this very interesting talk. Let us thank Oleksandr.
Thank you.
And we have time for questions. So, okay, Jan Ole, please unmute yourself.
Yes, hi. So I would like to ask whether the solitons are also stable under quantum fluctuations.
In principle, no, but the time that it takes a soliton to be dissociated is very much longer than for a breezer to be dissociated. So if you write down the actual, so the fully quantum model of a soliton, it will dissociate, but in a very, very long time, comparatively.
I see. How long do you know? So what
not
does
from
this
the
time scale depend on?
So not from the time of my head. Yeah,
okay.
I think, yeah, sorry.
Thank you.
We have a question from Varinder. Varinder, please unmute yourself.
Yeah. So hi, thanks for the nice talk. So in one of the slides, you have compared coherent states of harmonic oscillator with the soliton. So actually, what is the difference between soliton and coherent state? Because coherent state is also like that, its wave packet doesn't disperse with time. So what is the essential difference between them?
Well, I mean, if you put the coherent state in the in nonlinear Schrödinger Gospodyevsky, it will disperse with time, basically. So that's the solutions of different equations. That I guess my point is. And so yeah, here, yeah.
Okay. Since this coherent state is for linear Hamiltonian. So solution of linear.
Yeah, and specifically here, I just mean the ground state of harmonic oscillator in principle.
Yeah, it's just coherent state is a displaced ground state of harmonic oscillator.
Yeah, sure. Yeah.
Okay.
Yeah, but like the soliton, this 1 over cosine Hepulacus is the solution of the nonlinear Schrödinger equation. Yeah, so it's a different equation. It's a nonlinear equation.
Okay. Thank you.
Jan, do you have further questions? Okay,
yes,
please go.
In the meantime, I thought of another question. So since these, so is there like any proposal to use these solitons as some sort of qubits for quantum computation? Do you know if there is people trying this, or if there is like any serious obstruction to do this?
Well, I would say it carefully, I guess. So there are, I think people were thinking about and are thinking about this. The problem is the stability of the attractive Bose-Einstein condensate. It's you can create them, and they've been being created for quite some time now. But attractive BEC tends to collapse. So to have them, so the robustness of qubits would not be as good as for some other proposals. There are ideas how to use them in quantum information, I think. Right as of now, I don't remember something very concrete, to be honest. Maybe, but yeah, like just right now, I cannot recall anything. But I think the main problem is specifically for this system. So maybe in some other context that actually work better, that the system, the BEC with attraction tends to collapse relatively fast. You can keep it alive long enough to measure and to observe solitons, but to use them for actual quantum information, like for qubits, I think that's the main problem.
I see. Okay, thank you.
Thank you.
We have a question also from Dilip. Dilip, please go ahead.
Yeah, can you hear me, right?
Yeah.
Okay, so in this solitonic behavior that we have seen in the BEC, that is basically like one component BEC, I guess.
Yes.
So is there any signature for this quantum mixture, like two component BEC or something like that?
I don't think there were experiments for the quantum mixtures okay. What I'm talking here are bright solitons when it's the density peak. So there are also dark solitons, which is the density deep. On gray solitons, there are many different solitons, of course. So my point being, so for the mixtures of BECs to observe bright solitons, I don't think that the experimental works. Again, I think mostly because it's collapsed, you need two different species, it's harder to kind of maintain them. In just mathematical physics, the system of coupled nonlinear Schrödinger equations, they were definitely considered, and there were, for instance, there were Markov solutions where you have similar, the same interaction between gases. But yeah, experimentally, I don't think, not right now I can recall realization of bright solitons.
Yeah, so there will be lots of non-linearity factor. For example, like interaction between different species as well as mass factor, different mass factor also comes into existence.
Yeah.
So, yeah.
I think, I mean, no, it's a very interesting question. Like for not to include the mass difference, you can consider different hyperfine states. Like you have a quasi-spin of atoms, let's say. But I think there are just many experimental problems with that to realize that.
What kind of atom so far it has been done in experiment? Like
right. So here, for instance, so the Randy Hewlett group uses lithium-7 almost exclusively. I think for this experiment, I don't recall right now. Yeah, sorry, I'm blanking on it. Sorry, but I know that Randy Hewlett uses lithium. That's for sure.
Okay, thanks. Yeah.
Lithium.
We have also a question from Ming.
Yeah, thank you for your talk. Just curious about about this breather and soliton. So long time ago, I also read a paper, something called the quantum droplet, which is self-trapped BEC. Could you tell me what is the difference between this, I think, breather or stuff?
Quantum droplets are very interesting. So how do I approach it? So original proposal for quantum droplets comes from Dmitry Petrov, and I think it was in 3D. And so the idea is that you have a mixture of two gases, two Bose and Schenken, let's say, two Bose gases, and you balance the mean field contributions to the interaction such that the actual the main contributing factor to the interaction is the Li-Hong-Yang correction, so the quantum effects. And yeah, so it's a bit different physics. it can be related. So for some parameters, you can go from a droplet to a soliton. For example, there is a paper by Tulutki, in PRL from 2019, I think 18, where they kind of show how a droplet, droplet would have like a flat top, like a flat profile, right? And soliton, of course, doesn't. It has this thing. But you can, by varying the interaction between two components, you can go from one to another, I think. Another way to make a droplet is to consider long range, like dipole interaction, which would also balance the mean field, but would lead to the other contributing terms to be main effect, and then would also lead to droplets. But that I know a little bit less about.
Okay. Can I say that for this bright soliton or this droplet, both of them have this attractive nonlinear interaction, but for droplet you have like two components of BC.
So droplets, especially in the bulk, can be, so if you don't consider the boundary effects of this, can be described by basically, where is it? By also Gross-Petoevsky equation, so-called modified, or there's some other name for it, modified Gross-Petoevsky equation. Yeah. So, but you see, here is the third order nonlinearity, right? And so if you add the term which is a second order, so like minus kappa psi absolute value psi, that would be equation that describes behavior of droplets in the bulk, so like in on the top of it. Yeah. So it's a bit different equation. That's my point, I guess.
Okay. Thank you very much.
Thank you.
Do we have any further questions from the audience? Maybe let me ask just what is approximately kind of the number of atoms there in the experiments that you've shown in breeders?
Yeah,
thousands, or is it?
Yeah. So let me pick up the slides. Yeah. So here was 3,000 atoms, for example. So again, we used numbers close to the actual experiment for this calculation. They of course change, but like around several thousand atoms, I think, usually. Yeah. At least in the Randy Hewlett experiment. Yeah.
Okay. Then another maybe. So okay, is this is the breeder somehow related to a time crystal, or could you say that this is a time crystal or not, or why not? I mean,
okay, I know it's all the hype nowadays. Eh? Okay, I am not sure right now. To be fair, I think there's some connection to it, but I haven't looked into this that much. I don't think it's related directly. I think you can relate them in some way, but because so for time crystals you have a driven system that, for instance, that's kind of a can oscillate with twice the frequency, and so here the frequency is given just by the parameters of the system. So I don't think that there is a direct connection with this. Why I'm kind of doubting myself is because I seen a paper talking about this like a few weeks ago. I don't remember what it was really about. I don't think I read it like very more than abstract, but I think there was something about it. So I might be wrong here.
But you said, so one of the things with time crystals is that there should be some resilience to perturbation. So here somehow you have to, you said you have to have the combination of two solitons fine-tuned, right? So if you move away, then you get, I mean, part of...
Yeah, so Bose, so a soliton is resilient to perturbations, yes, but Bose, especially nonlinear Schrödinger Bose, is not, because, as I said, like it can be easily separated into two. Like here we show that it's quantum fluctuations that can separate it, but before we had a work where like very, very narrow potential, external potential, just hit Bose in different spots in different places. And that would also separate it into solitons. So you don't need that much energy to separate them, basically. Yeah. So it's in this way, it's not resilient, in a way that you mentioned.
Mm-hmm. Okay, thank you. Any further questions or comments from the audience?
Let me ask one question again. So at the very end, you concluded that breather quantum fluctuations destroy the breather on some time scales. Can you reiterate, please, first of all, what is happening? Are the atoms just flying off out of this? Is that what happens in the real system? And what can you tell again what determines this lifetime?
Well, what happens in the real system is the question that is being. I mean, the experimenter works to try to include this in the experiments. But yeah, so how do I put it? So in principle, I guess you can consider that solitons in a breather are entities in themselves, and so there are fluctuations of how velocity, relative velocity of those two solitons in a breather, and due to that, so there is a chance that they would just separate. I guess that's the kind of intuitive way to put it.
In this expression here, I think we talk about the dissociation time, right? That's the time.
Yeah.
Right. So what I see what the enumerator how it looks like, but what about the denominator? Can you remind what this square root finally, how is it expressed through the parameters of this?
So yeah, I mean, so for instance, calculating the initial variances of the parameters of the relative velocity. Yeah, so it depends on the number of atoms, and the bar is just a unit. It's a unit of velocity. Okay, and that's so in principle, this time depends. This time depends basically on the number of atoms. Yeah.
So it looks like that this dissociation time becomes smaller and smaller the larger the number of participating atoms. That would be a bit strange. Well, unexpected at least.
I mean, so the numerator also depends on number of atoms. So,
yeah, that's what I'm saying. So the numerator gives me 1 over n, and the denominator seems to give me another square root of n in the denominator. So I have an n to the 3/2 in the denominator. And so for n going to infinity, tau should go then to 0.
So it basically separates immediately. Yeah.
But n to infinity would intuitively be the non-quantum limit, so to say. Classical limit.
Yeah. Yes.
So it looks like I have a prediction.
Yeah. Okay. I need to think about this a little bit.
And then you also mentioned that the single soliton, so not this bound state of 2 solitons, but the single soliton is also expected to be unstable under quantum fluctuations. Can you quantify this time scale in some way, or?
So there is a paper by House and Fly, I think, that actually does all these calculations. I just don't remember from the top of my head the dependence on n on other parameters, but yeah, that's something that's been done quite some time before. Yeah. Yeah.
Thank you.
Okay, so if there are no further questions from the audience, let us thank Oleksandr again.
Thank you.
And with this, we conclude our today's session.